Hi, this is Joyce McGill, and I'm giving my lab report for Lab 7, which is about parallel and perpendicular forces. So first, the problem given in this lab was to find the orbital path of a star that's orbiting around a black hole, and to find the mass of the black hole. So the main result was that, as you can see here, the star went in an elliptical orbit, and the mass of the black hole was approximately 1.98 times 10 to the 31st kilograms. So the physics principles used in this lab were, of course, the momentum principle, which states that dp dt is equal to the net force, and also this equation here that the net force is equal to the perpendicular net force plus the parallel net force, which, based on the momentum principle stated above, we can come to the conclusion that dp dt is equal to dp dt parallel plus dp dt perpendicular. And then this equation just breaks up the parallel and perpendicular dp/dt's respectively. So we used the data that was given from Star Data that was downloaded from WebAssign, and it just gives the points of where the star is located at various times. And you can see here on the right, I plotted out this data, and then this in the middle is the path of orbit based on the VPython data. So this is just so that you can get a better picture of the fact that VPython is a pretty good estimate of the path of orbit. So you can see this blue line is the experimental data, and the red line is the calculated data, and so it fits pretty well. So I'm just going to show you my code real quick. Just going to run through it. So first, of course, you have to put in the mass of the star and the position of the black hole. This just extracts the data from Excel. Here you calculate the velocity, and then if we go down a little bit more, you can see you calculate the initial velocity and the final velocity so that you can calculate the initial momentum and the final momentum, which you then use to find delta P, which is final momentum minus initial momentum. From there, you calculate dp dt, which is just the change in momentum over the change in time. And based on the momentum principle stated before, the net force is equal to dp dt. So then you have to calculate p hat and the magnitude and such so that you can find the parallel and perpendicular net forces, which you do in these steps here. And then, of course, you just find the position of the star and the mass of the black hole, so that when you run it, this is what it looks like. So this red arrow here, it's kind of hard to see, but that gives the parallel force. This blue line is the perpendicular force, and the black arrow is the net force, the total net force. So what does it mean? We know that due to the momentum principle, dp dt is equal to the net force. But it's important to remember that there is a difference between the two. dp dt is a calculation based on concrete data, so it's tangible, whereas the net force is an estimation based on the momentum principle. It's more of a conceptual value, it's not actually tangible. So based on that information, we know that the parallel dp dt is equal to the parallel net force, and the perpendicular dp dt is equal to the perpendicular net force. And as before, both the parallel and perpendicular dp dt are based on concrete data and they're tangible, whereas the parallel and perpendicular net force are conceptual. So what if the black hole were replaced by another black hole in the same location and the motion of the star remained unchanged? Then what would happen is you would not be able to find a mass of the new black hole that is different from the original one. So why does this happen? Well, based on this equation here, that the force of gravity equals the negative gravity constant times mass 1 times mass 2 over the magnitude of r squared times the unit vector of r, we know that the mass of the star remains unchanged and the path of motion remains unchanged. Therefore, because neither of those values differ, the mass of the black hole will not change either. So that's the end of my lab report on parallel and perpendicular forces.